Today I'm going to discuss the precise angle control on our medium current implanter system. It's established by two basic measurement components. One measures what we'd call the vertical angle, the tilt angle, the VBA as we refer to it, vertical beam angle. And the other is the horizontal angles in the scanned plane of the beam. The first, the VBA component, has a combination of the electrostatic chuck on the front of the component with a collimated Faraday on the back. And when the angle is to be measured, this unit flips over so that the collimated Faraday is exposed to the beam. It rocks back and forth through about 6 degrees, optimizes and identifies where the maximum beam current is, identifies that as the actual tilt angle of the beam, and corrects for it. Then that fixture flips over, the electrostatic chuck with the wafer on it is now exposed to the beam, and the corrected vertical beam angle is implanted. Horizontally, we have the scanned beam in the horizontal direction, and a mask is imposed in front of the beam with 6 slits in the mask. The profiler moves across the back of the mask, identifying the location of the beam as it goes through each one of those masks, the mask slots. To the extent that there's some deviation from where it should be, the angular offset of that deviation is calculated and corrections are made to the beam with the parallelizing lens and or the steering electrode further upstream. So those two basic components are what we have for in situ identification and correction of the beam during the auto-tune sequence and prior to the beginning of implants. So the real question is, how does angle affect the device performance? Why are we interested in angle control at all? Well, there are two basic categories of implant conditions that are sensitive to the implant angle. One is, for example, with a 0-degree tilt implant, where the beam is coming in normal to the surface of the wafer. In that case, you've got geometric features, the device structure on the surface of the wafer, and the beam should come down, be the device structures or photoresist masking. The beam should come down parallel to the surfaces of these features and make a nice precise implant into the silicon. To the extent that the beam's off in any direction, you'll have shadowing on one side of those devices and under implanting on the other side, neither of which is particularly desirable. Additionally, for these 0-degree tilt implants, we have a condition called channeling that can occur, which is the beam coming in aligned to a preferred direction in the silicon structure. That channeling allows the ions to penetrate deeper while at the same time doing less crystal damage. Both of those characteristics, differences in depth and differences in crystal damage, can have substantial effects on the device performance. So even for a 0-degree tilt implant, the characteristics of device shadowing and channeling can substantially affect the device performance. But there's another different category of implants we do, which has to do with altering the characteristics of the end of the gate. When we normally do an implant, we have source drain implants on either end of the gate structure. Now, these implants, because of the scattering characteristic of the original implant, can have a straggle underneath the gate somewhat, and additional thermal processes can introduce diffusion underneath the gate. So there's going to be a little bit of source drain implant underneath the gate to begin with, but that's largely uncontrolled and a result of the basic physics of the implant and thermal processes that we can't modify. What has been found is that by tailoring the boundary between the source drain and the channel underneath the gate, we can modify significantly the electrical characteristics of the transistor, threshold voltage and such, in very profound and substantial ways. Some of that's done by source drain extension implants, but another one that's of particular use for medium current implanters is called a halo implant, where intentionally we come at a fairly steep angle, which can be from 25 to 35 degrees, under each side of the gate and deposit dopant at the end of the channel to modify the characteristics. And that can have a profound effect, again, on the characteristics of the transistor. What these implants are very sensitive to, especially as gate lengths shrink, is the angle of that implant. Again, like I said, these implants, depending on the device and the particular characteristics of the device, can be anywhere from 25 to 35 degrees, but they have to be controlled very carefully, because a 1 degree variation in this implant can affect threshold voltages, for example, on the order of several percent. So in the old days, when angle control might be limited to, say, plus or minus half a degree, plus or minus half a degree, say on one machine plus half degree, on another machine half a degree, you've got this 1 degree variation already. And that will allow these multiple percent variations in threshold voltage. So we would like to be able to control the halo implant much more tightly than these 1 degree limits. So while the requirements for halo implants are such that better than a 1 degree control is desirable, we have identified in our testing over an extended period of time, almost 6 months, that we're able to achieve control better than 1/10 of a degree in some cases. So it appears that we're well within the requirements right now, well within the requirements for what are needed for most halo implants. So in effect, what we're finding is that while previously controlling for dose, energy, and species would often be sufficient for good manufacturing control, what we're finding is, because of these unique characteristics of 0 degree tilt implants and halo implants, that for good manufacturing control, we really have to have these angles under very precise control, and that the limits we've had in the past are simply insufficient now. And that 1/10 of a degree type control has to be established, and we've been able to demonstrate that. The constant focal length scanning characteristic of our end station is fairly unique to our system. What it involves is, as the beam transits the end station, it can change its size and angular characteristics. And with the constant focal length system, we have the beam at this position, and the wafer scans through the same location of the beam in this fashion, instead of scanning vertically through it this way. If the beam scans vertically this way, then the bottom part of the wafer will see a different beam characteristic than the top part of the wafer, altering flux, for example, from bottom to top of the wafer. The way we do it, all parts of the wafer see exactly the same beam characteristics, and should provide better top to bottom consistency. The angular energy filter is one of the unique aspects of our medium current implanter. What it does is it's a pair of electrostatic deflection plates at the end of all the acceleration or deceleration of the beam. These electrostatic deflection plates deflect the beam down through 20 degrees. After the deflection, there's a pair of horizontal slits that provide a energy resolution, so that what's achieved is that only the on energy component of the beam, if there are any off energy components, is deflected through these slits. Any neutrals that were in the beam previously to that go into a beam dump. Any off energy components, either higher energy or lower energy, are not deflected through those slits and thus are filtered out. It's an extremely effective way of ensuring that the energy accuracy of the system is extremely pure. On our system, the parallel scan pattern of the beam is produced by an electrostatic parallelizing lens. The unscanned beam enters a pair of horizontal electrostatic deflection plates that produce a fanned shaped pattern of scanned beamlets, which then go through the parallelizing lens and are made parallel. The focusing characteristics of the parallelizing lens can be altered by changing the voltage on the lens, which will produce either overfocusing or underfocusing, and thus can be used to alter the angular characteristics of the beam. Additionally, upstream of the X-scan plates, we have a steering electrode which can alter the position of the focal point, which can skew the whole set of beamlets in one direction or the other, allowing additional focusing capability on the beam. So during the auto-tune sequence, these two parameters can be adjusted, both the parallelizing lens strength and the steering electrode strength, to alter the characteristics of the beam angles in the beamlet, which are being measured by the HBA measurement during auto-tune.